ARRT, digital radiography, about the technology behind the flat panels that are used in digital radiography, about the three different types, both indirect and direct, and then there's two types within the indirect flat panels that we're going to be talking about today. Stick around all the way to the end. We're going to talk about a comparison between them, so you're going to know about how they work and how they compare relative to one another. Also, if you're new to this channel, click down below on subscribe and click on the little bell icon so you get notified when we have more content that's interesting about radiology. So direct versus indirect, those are two different types of flat panels. Direct, you're skipping a step. Indirect, you have an extra step, and that extra step is actually generating light. We'll cover indirect flat panels first because those are actually more frequently seen within the clinic. Indirect flat panels also have two different types within indirect flat panels depending on how they're read out. So you can have either an indirect flat panel read out on a TFT or a CCD. We're going to cover both of them. But both types of indirect flat panels, they start with one thing, which is a layer that we call a scintillation layer. And that's the layer in which the X-rays are going to come down, they're going to interact with that scintillation layer, and out from there come visible light. Visible light's coming out after the X-rays interact with that scintillator. You have a couple of different choices. You have a gadolinium-based scintillator that a lot of times is referred to as GOS or GADOX, but the gadolinium-based scintillator has good light output, but the light is coming out relatively isotropically in kind of a cone coming out from where the X-ray interacts. And the idea is that that is blurring the signal. So if there's an alternative that could do less blurring, that would be desired, and that is actually called cesium iodide. So it's a crystalline structure where the crystals are grown in columns. So because the crystals are grown in columns, when the X-ray comes down, interacts, then the visible light is going to ping back and forth between the sides of the column more than it's going to spread. And in that way, you get higher spatial resolution because there's less light spreading. We're going to first cover the TFTs. And a TFT-based panel, you have your visible light being generated, and then in order to convert that visible light into a signal, you use a silicon photodiode. So the light comes down, that visible light interacts with the silicon photodiode and generates a current. That current from the silicon photodiode is an electric analog signal, and coming out that electric analog signal, we need a method to digitize it and to separate that current out into the individual detector elements. So the first option is to use a TFT, or thin film transistor array. So the TFT array consists of a glass substrate on which different things are essentially etched or built into that glass substrate. And it's typically done based on silicon. And the idea is that there's an active area within each detector element. There's a capacitor within each detector element to store the charge. And then there's a gate or switch within each detector element in order to say when we're going to address and want to read out the charge that's stored in that detector element. So you have, again, light coming out from the generation process in the scintillator. That's measured in the photodiode. And then the photodiode is converting to an electrical signal. That's going to be measured in your active area of the TFT array. And then when you want to read out the given signal, it's going to be, there's going to be amplification process, and then there's going to be analog to digital conversion so that we can read out a digital signal for each of those detector elements. So the TFT arrays is the same technology actually that's in your flat panel displays. In your flat panel displays, the individual addressing of each of those elements is actually used to turn them on and off, such that you can say, yeah, you'd like to have light going on in that pixel on the display. Likewise, we can use other technology that's in your cameras, namely a CCD, and the CCDs are very good at detecting visible light, right, and converting that to signal. So that's something we want to do here. After we have our scintillator, we could convert that visible light to a signal. But the problem is the CCDs are relatively small. So you have a relatively large flat panel and a relatively small CCD. So you need some way to essentially demagnify the signal, that visible light signal. There's different options, including lenses and fiber optics. But the idea is you want to bring that light and collimate it down to a smaller size. The CCD array can convert the visible light signal to the electrical signal, and then it can convert that electrical signal and read it out as well. You don't need that additional step of the silicon photodiode that you had in the TFT array. The one thing is that we need the light to be collimated down, and so that's going to happen more easily if the light is more forward focused. And so the cesium iodide is going to be preferable for CCD-based arrays because you want the light to be more forward focused, whereas in the GADOX-based scintillator, it was more diffuse. The part about understanding the direct and indirect flat panels is to hit the like button down below so that you can pay it forward basically so that more people can see the video and learn about the direct and indirect flat panels. Now we've covered both the types of indirect flat panels, and it's time to go on to the direct flat panel. So the direct flat panel, the physics is a little bit different. We're skipping that stage of generating the visible light, and we're going to go to electrons directly. So you have an amorphous selenium layer that's the size of your flat panel. The X-rays come down, they interact with that amorphous selenium layer, and they're going to generate both electrons and whole pairs. So if we apply what we call a bias across that selenium layer, there's going to be a positive charge at the bottom and a negative charge at the top, and then we can pull the electrons down, and as we pull those electrons down, the flow of electrons is actually just an electrical current. So that flow of electrons, that electrical current, can be measured directly using a thin film transistor array. The same thing we talked about in the indirect flat panels, we can have one of those behind our selenium layer, and we can measure the signal directly there. So in comparison with the indirect panels, we get to skip that step of having the silicon photodiode because we have electrons measured directly. Once those electrons are coming in, they're going to be measured within the active area of the TFT array. The charge is going to be stored in a capacitor for each of these detector elements, and then the switch or the gate is going to be used to address each of the detector elements and to read each detector element out. The major advantage of direct DR flat panels is higher spatial resolution, because those electrons that are coming down, they're going to get pulled down relatively directly, will not spread out. Whereas the light photons did spread out in both cases, in the cesium iodide and the GADOX case, the light photons did spread out. It was less in the case of cesium iodide, but the direct panel really has the advantage in terms of spatial resolution because there is less spreading of the electrons as they're going to be coming down and measured. Now we get to the comparison. We're going to be talking about your three big choices. Again, a CCD, TFT arrays for indirect, or the direct measurements with flat panel systems. So depending on what your task is, if your task is mammography, where spatial resolution is of the utmost importance to be able to see those microcalcifications, then you're going to want to go with the direct flat panel. You're going to get the highest spatial resolution out of that type of system. And so if you can't afford it, those are going to be the most expensive systems. The readout is not as quick, so it would not be as good for a system that needs to do angiography procedures, for instance. The other reason that the direct flat panels are not as great for large patient imaging is that they are better at detecting lower energy x-rays in comparison with higher energy x-rays. So for mammography, you're gonna wanna go direct flat panel. Then for general radiography, you have the choice between CCD and TFT arrays. The TFT arrays are more common within the field. They are gonna be a little bit more dose efficient because you're not gonna lose any of the photons in the light demagnification process that you have within a CCD-based system. But the CCD-based systems in general will be a little bit less expensive compared with a TFT system. So at a high level, you have that trade-off of dose efficiency versus expense. And in general, the TFT systems are the more common systems for general radiography. And then for mammography, you're gonna wanna go with a direct flat panel. Finally, there's another option that we didn't talk about here, which is called CR. It also actually does use a digital signal in the end. And we're gonna have a video coming up right here in the link once it's ready.
Alright, I warned you about the guy. But I like the diagrams and it is accurate information. But Marissa, if you think of a better video that you want to share on your side, feel free to do that whenever. Alright, so let's get going. Where are we starting at here?
Can you go back? I found two different, for the CR. Can you also use the charge coupled device for
Yes.
CR? Okay, so you can use it for the CR and then you can use it for the DR indirect conversion.
Correct.
Okay, for both of those.
I have a question. Where did the gadolinium come into play?
Gadolinium is going to be an entry point, so you can have a gadolinium layer on the indirect. Used with a CCD. It's not as good as that psyllium, that's what he was talking about, that amorphous psyllium, because it comes in columns. But you can use gadolinium. And if you hear the term gadolinium used with contrast, it's usually paired with MRI. So that's a really common contrast agent used for MRI.
So is that gonna be the scintillation layer?
Yes.
So that could
Or
be
the indirect for CCD.
Okay.
That's an alternative method, gadolinium,
Okay.
that you can use for that layer. All right. So let's start out in the first section here. So we've got imaging equipment. So we have X-ray generator, transformers, and rectification systems. What do you guys have? I'm gonna try to find my place here.
You want to do like the general breakdown?
Yeah, did you guys draw a picture of it? What did you guys do? Or what do you guys have written down for this information? Do you have tube construction or something like that?
I had two.
You drew a picture?
Well, just because I did that PowerPoint, I just.
Oh, yeah. Oh, you were supposed to present today.
No,
Oh.
I was supposed to present next month.
Oh, next week.
No, next month.
Oh, for original image production.
Yeah.
The original date for it, okay,
Yeah.
that makes sense. I think we have a lot of, presentations the last few weeks of class too.
Yeah.
That was on this material. So, it'll be good, it'll be a good recap for you. Alright, so what do we need to know about the X-ray generator, the transformers, and the rectification system? Let's break it down. Basic principles.
Right, we got 3 circuits, primary circuit, secondary circuit, filament.
Okay.
And then we have our currents, which is where the transformers come in. So we
Okay.
have alternating current comes from the power company,
Good.
but the tube can only use direct current. And so the transformers and the rectifiers, but the transformers can only use AC, so you have to rectify it.
Correct. Good.
And, yeah.
Okay, we have to have AC or there's no induction. Remember, we have to have the alternating current or there is no induction. So normally we have that pulse, 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 pulse. And then do we need anything else for basic principles of the generator, the transformer, or the rectification system? Everybody feel okay with that? It's really broad. I think it goes into detail a little bit later, especially when we start breaking down the components. Okay, so how about phase, pulse, and frequency? What do you guys have for this one? Phase, pulse, and frequency of imaging equipment.
Single phase, and then three phase, and then the high frequency.
Good. Single phase, three phase, and high frequency. Okay. Do you guys know the numbers associated with those?
There's like a 1% ripple, 13% ripple, that's what you mean?
Those ripples are good too, yep, with the pulse frequency.
So the single is 1, and then the other one, it differs from book to book, but the last one is I just go 1.4 for sure.
Yeah, I'm trying to think of what, I think they're in this book, because I don't see them in this category. I don't see it the way that they're actually breaking it down. So they actually have Ohm's law in here as well, under basic principles, so under electrical circuits. Do you guys remember Ohm's law? What is it?
I times R.
V over I times R, good. So remember, if they give you intensity and resistance, we're solving for what?
Voltage.
Good. And if they give you voltage and intensity, you're solving for what? Resistance, good. So it just plugs in a triangle here. So Ohm's law, the V is gonna be at the top, I times R. And then let's see what else we have here. Before we pull up those numbers so that I don't see them in here. Oh, here they are.
So this is the phase and pulse.
Mm-hmm. All right, so the numbers that I have from this category book are 1 heat load unit for a single phase. I have 1.3 for a 3-phase at 6 pulses. I don't know if you have them or not. 1.41 for a 3-phase 12 pulse, so 12 pulses, faster pulsing here. And then 1.61 for high frequency. So that's gonna be for tube loading, I'm sorry, that's the next
I think
section.
there's a section on that.
There is, it's right after this one.
So what exactly is this, this is heat energy?
So those are the numbers that we calculate for heat load units. Heat load units, yep. Heat load units, so depending on what type of generator you're working with. Are you working with a 1-phase, a 3-phase, or a high frequency pulse? So depending on what type of generator you're working with there.
What do we use in our rooms? We use high frequency?
Most of them are gonna be high frequency, yes. Unless you're working with older equipment, you're not gonna know what type of generator you're working with. And you're never gonna walk into a room and say, oh, what type of generator am I using today?
This is heavy as hell.
Right, nobody's ever gonna know. No one is ever gonna know. You're not gonna ask questions like that, but we do need to know this kind of stuff for the registry. All right, do we have anything else for phase, pulse, and frequency? The Kettering book kind of breaks down what a sinusoidal wave is. Everybody remember the waveform? When we're above the line, we're positive. When we're below the line, we're negative. Remember all the properties that they could ask you. So wavelength, amplitude, frequency, velocity. If we're talking specifically about x-rays, which I think they would, since it's a registry on x-rays, they might ask you what the velocity is of an x-ray. What is it? Speed of light, good. Speed of light, and it doesn't change. We can change the speed of the electrons at production, but we cannot change the speed of the x-rays. We can't change the speed of the x-ray. All right, do we want to know or talk any more about phase, pulse, and frequency? I kind of have what Heather already said. A generator is a device that converts mechanical energy into electrical energy. Each pulse possesses the same peak electromotive force, or EM force, EMF sometimes it's noted. Each pulse varies in the direction in which the EM force is induced when the armature conducted into the external unit. So we're talking about the external circuit now, when we talk about this kind of stuff.
Are we gonna need to know like what components
the diagram, yes. I would definitely know the diagram. Did you guys go over that in physics two? Or physics one?
Hard to say.
Okay. All right, the X-ray circuit. Do you want a picture of it? I can go make you a copy of it. Okay. All right, let me go make you a copy of it. I'll go right next to it for you. So you'll see me. Okay. All right, so I gave you guys a picture of the circuit. Someone asked me, what kind of questions could they ask you specifically on this? So they could ask you, is the auto transformer located on the primary or the secondary side of the circuit? Okay. Is the a sample question, is the auto transformer located on the primary or the secondary side of the circuit? Primary. Okay. They could ask you to label the auto transformer. They could say, move your mouse and click on the auto transformer. So do you know where it's at? They could also use the term low or high voltage. So they could say, is the exposure timer on the low or the high voltage side of the circuit? Okay, it's on the low, so we're looking around 11. So know how to label this, know what the parts do. I'm not gonna go into detail in this because this circuitry stuff is about 2 weeks of material. But all of these pieces that we need to know, you need to know the flow, so how it's going, so that's why it's numbered. 1 starts at the AC supply, 2 is the master wall switch, 3 being the fuses, 4 the line voltage meter, 5 auto transformer, 6 line voltage compensator. So we need to know all of the parts, where they're located, and which side of the circuit they're located on. Okay? And we're gonna go over it again in Kettering. I don't think they're gonna spend a lot of time on it again though, because I think these circuit questions are phasing out a little bit more. They want us to focus more on the digital aspect and how the image receptor is working versus the electronics, because we're not electricians, right?
Yeah, that's
We
what I'm
can't
asking.
fix
Why
a
do we-
circuit.
Why do we have to learn all this when we don't literally do anything with it?
So we're not gonna change it, but we do have to know how we get to the actual x-ray. So that's the process behind it. So what's happening? How do we have an x-ray exposure? That's why they make you learn the foundation of it. Do I think they should go as heavy into the electricity
No.
and the laws of electrostatics? No, but like I said, it's phasing out. There used to be even more than this, so they're slowly chopping it off a little bit, piece by piece. But I wouldn't, if you aren't familiar with this, I would definitely know how to label it. I would know what each piece does, what side of the circuit you're on, whether it's high or low voltage, and, let's see, how to label it, what each piece does, and if you're on primary or secondary side of the circuit, and the order of the flow. Those are the 4 main things I would know for sure. Okay? I don't even think we're there yet on our study guide, but I saw that little diagram in there and I thought that would help you guys.
Do you even know how much, voltage is coming into that 220 number?
The 220 I would know because we typically use 220 in the US, and maybe a 60 cycle alternative current, 60 cycle AC unit is what we use in the United States. I would know those basic numbers. I know this electricity stuff is not the best, right?
Okay, just make sure, so with if you have for the transformers, you have the high voltage and you have low amperage. You have low amperage, you have high voltage.
Correct. Depending on if you're using a step up or a step down transformer.
And that's why we use these step up comes first and then the step down comes second.
Correct. We amp it up, then we bring it back down so we don't start a fire.
Okay, I can remember that, but don't start fire.
Yes.
I did.
Yep. All right. I also have in here, in this little section of, so I guess I'm in that section. Hold on, I just don't want to go ahead and skip anything here. Okay, so I don't really see a section on this, but this is where Kettering put it in. So I don't know if I'm going ahead or not. But I have types of electrical circuits. So I have the X-ray circuit, and then I have types of electrical circuits. Did you guys put this in your notes for this section?
No.
Parallel versus series, do you remember these?
Yeah.
Oh, what fun. I think they actually have a chart in here. Do you want me to make you a copy of it if we have
Yeah.
one?
Aren't we just, is it in the book we're gonna get?
Yeah, we're gonna get it.
Yeah.
It is not in the book.
Oh, that's good.
They just give you sample problems. No, so which one do you need to add, which one do you need to multiply, which one do you need to reciprocate? Do you guys remember that, parallel versus series? No, does anybody have their physics books? That's where the chart is, it's not in this book. Anybody have a physics book? No?
I rented a lot of my books, so I had to send them back. Not the one trainer books, not the important books, the physics.
They're all, the physics book is important. Yeah, this isn't your physics book. Alright, I might have to get you guys one later, cause I don't see one on here. I can post a page number in Canvas of where to locate it in your physics textbook. But they don't give me the laws broken down right here, and I don't know them off the top of my head for amperage, resistance, or if you're calculating volts, if you're using a parallel versus a series circuit. So what is the difference between a parallel and a series circuit? I know you didn't look this up, but do you remember? Right, so series, you can, I don't have a board either. Series you can think of as just one running strip, like Christmas lights, right? Parallel is gonna have multiple circuits running through it. Multiple circuits running through it. The way they describe it in here is a parallel circuit. The components of a parallel circuit are connected off as branches to the main circuit. So you might have multiple resistances, multiple voltages being documented. Whereas in a series circuit, you're gonna have just one square. They might give you a square, or they might make it a circle. So one solid shape. So if it's a series, it's running in one line. So if you have one part of the series that breaks, or one cutoff, one clasp in it, you would not have a correct full unit here. So you wouldn't have any way to connect the electricity. But in a parallel, kind of like DC current, yes, kind of. If you want to compare it to that, I see what you're saying there with how it's directing, yeah. But in a parallel, you could have one of the voltages stripped or one of the resistances stripped or a break in the current, and you would be able to continue with the electricity, so you would still have a line.
So it's like the old Christmas lights, if like one bulb goes out, the whole thing is out?
In a series, yes, in a series unit. A series is gonna be a circle or a square, one strip, whereas a parallel is gonna be a main strip, and then it'll have many branches coming off of it. So you'll have smaller rectangles. I'll post the page number, or I'll take a picture and post the chart. I don't have my physics book in my office because I don't have any furniture over there. So when I find that page number, I'll post it for you guys for following the rules and solving. So if they give you one resistance or one voltage or 1 amp, you have to be able to use the rules of parallel versus series to solve it. Does it sound familiar to you guys? But you just don't remember it? You guys didn't look it up? I think it's in one of the early chapters, like maybe 2 or 3. The laws of electrostatics is where it's at.
Laws of electrostatics.
Yeah. But I'll post the page number and I'll post the chart for you guys, so you guys can review it. It's very simple. You either add them all up, you multiply them, or with the one, which I think is reciprocals of a series circuit, you have to reciprocate them and then multiply them out. So if they give you many reciprocals, it's a little bit more, but there's only one tricky one, and that's gonna be the series resistance. So I'll post the numbers for you guys. It's just common rules to memorize for parallel versus series circuit. And I know it's not in here, but Kettering included it under tube loading and components, so that's why I wanna make sure that you guys know it. Alright, I'm gonna skip through the X-ray circuit information. You guys are gonna get this book. It does break down which piece does what. I would definitely review this before your exam next week, cause I know I have a couple questions on this. Alright, components of a radiographic unit, fixed or mobile. So what do we have for operating console? I know we kind of already went over this for radiation safety, but what is an operating console? Control panel. Is it in or outside of the X-ray room? Okay, good. Can it go inside the X-ray room? No, it's fixed. It's supposed to be at least, right? So you're not supposed to be able to take your own X-rays. That's the purpose behind that. What can you do on the operating control panel or the operating console? Mask KVP, take the exposure, rotor. On some, you can also turn the light on, right? So you guys are working with really fancy equipment these days. That's very basic. How about X-ray tube construction? So do we need to go over these, or do we feel good from radiation safety? We have electron source, target material, induction motor, and filtration. Do you guys want to talk about those again? Do you feel good? I feel like we went over them pretty detailed. Electron source, we know that we have to have an electron source that comes from which side of the tube, cathode or anode? Okay, good. Flows only in one direction, or we would have an explosion. Target materials, do you know what the anode is made out of? Good. So you have to have what for characteristic interaction? What energy? More than 69.5. More than 69.5 to have some kind of X-ray production with the tungsten at a characteristic interaction, so not a Bremse. Induction motor, what is the induction motor? Do you remember? What are the pieces of the induction motor?
Stator and rotor.
Stator and rotor, good. Sometimes they'll include the bearings in that as well. We know that which piece of the induction motor is external to the glass envelope? Stator's good. I feel like that's kind of where they're.
The revolutions, those numbers.
Revolutions per minute? I don't know them off the top of my head. I know that 10,000 is max.
Okay. But do you think they want us to know a number?
I think they do want you to know a number. It's probably within this book somewhere too. Revolutions per minute of the anode. Does anybody have the range? I think it's 2,500 to 10,000, if I'm guessing off the top of my head. 3,600 RPM? 3,600 RPM to 10,000 RPM. That's your range. Okay, and then filtration, we have what types of filtration?
Added in here.
And then the one that includes both? Total, good. Added, inherent, and total filtration. What does filtration do to the X-rays?
It takes out the low energy X photons.
Good, takes out the low energy photons, it filters them out. All right, AEC, we talked about a little bit as well. Do we wanna go over this? We feeling good about it?
We had that the last one.
Okay. I think, did somebody present on that too? Maybe not. AEC for safety? I feel like somebody presented on that. What is the main purpose of an AEC? Patient protection. Good, patient protection. So within that, we have radiation detectors. Those are gonna be the gas ion chambers that actually time it out. The backup timer is gonna be preventing your patient from being exposed for a certain number, or a certain period of time to protect them. We talked about the exposure adjustment that's built into the AEC. +1 or -1, +1 meaning more density, darker, -1 meaning less density, lighter. Minimum response time is going to be what? What do we have for that? Good, the time it takes for the system to respond, so you're just waiting for the system to turn the AEC on. Waiting for those gas chambers to fill up. Once they are filled, the backup timer stops, or the backup timer starts to prevent the patient from being overexposed.
When would you change the density if this is the patient's included?
The density changes on the AEC are built in. We can change contrast on our actual console.
So we're not ever changing.
You can change the density from +1 to -1, but I think what they're talking about here is the automatic, within the automatic exposure control. No, we don't modify density, you can, but we don't do it anymore because we focus on contrast, which is light to darkness, rather than density, which is only darkness. Or we talk about brightness and post-processing. That's kind of like an old school kind of thing. Manual exposure controls. What do you guys have to know? Manually changing the exposure. How simple, right? Manually changing the exposure. When would you do this? Good. Larger patients. How about smaller patients?
Yeah.
Smaller patients, right? If you're being equipped for pediatrics.
If they can't like hold their breath or something, if they're on like a ventilator.
Good. If they're on a ventilator, you could do this. If you had a wiggly pediatric patient, you could do this. If you had a Jerry patient that wasn't able to hold their breath, you could do this. Lots of scenarios where you could use the manual control factors. Old school portables used to be all manual. Now you guys have the nice APR built into it, so you normally don't even have to select a technique for that. Another time you might do a manual exposure control is if you have some kind of metal or foreign body built in. So if a patient has a femur, a metal femur, or some kind of metal running down from their hip, from a hip replacement, you might want to use a manual technique because the AEC is going to detect the metal piece and it's going to overexpose your image, thinking that the whole body part is made out of metal, right? Because that's what's going to be centered. I think they just want to kind of get your mind thinking, when would you use a manual exposure control? And you're already doing that clinically. You've been doing it for almost 2 years, so you know how to do it. Okay, then we break down image receptors. Image receptors. So first we talk about CR. So let me find my place here. What do you guys have for this? For CR, it gives you two things here, the plate and the plate reader. So let's talk about the plate first. What about the plate with CR? Do we need to know? PSP, good. What is PSP? Photostimulable phosphor. Okay. Layers of it, do we need to know anything else about the PSP? I would know the layers.
Places electrons at a higher level, conductive level.
Good.
They're trapped until they're placed in the reader.
Good. They're trapped until they're placed in the reader. So you have no image populated until you scan it through. Raise your hand if you have worked with CR. Hopefully everyone. There are some people that haven't. Raise your hand if you have not worked with CR. Okay. So it could get confusing if you haven't seen it before. So it's not as ancient as film, but you do have the actual image receptor that you need to run through the scanner for it to be able to populate the image on the screen, so almost everybody has. What does the actual scanner do, or what does the actual reader do? The plate reader.
It scans the PSP, laser scanning allows electrons to relax into lower energy levels in the phosphors.
Good. So when it's exposed to light, photostimulable phosphor, PSP, when it's exposed to light, then it reads it as an image. It has to expose it to light. So when you put the image receptor in the scanner, it takes it down. If you look down in there, if you are still using them, you'll see a laser light. It'll get really bright underneath there as it's scanning, and then you'll see your image start to populate. No one likes to work with CR anymore, right? We like the digital imaging, DR, indirect, or direct, whichever one we can get. But you might end up working with CR if you get a job right out of school, because it's not obsolete yet. So you need to know how it works and how it's utilized.
You say we need to know the layers of the PSP?
I would know the layers. It gives you a picture in this book. I'm not sure if it's in here or in your physics book, because I haven't taught from that book yet. If you want to write down the Kettering number, you can though. It's C65. So there's a protective layer, there's a phosphor layer, there's a light reflective layer, a conductive layer, a support layer, a light shielding layer, and then the barcode and the backing on the end. Does she have the picture? C65. C65. Alright.
Miss Olson,
Uh-huh.
just taking it back a little bit.
Uh-huh.
Grids, it's a whole bunch of pictures here.
Grids? I think
on
grids-
C29,
C29. I think grids is covered later in this section.
Okay.
It is.
Do we need to know, these pictures here? Do we,
What pictures?
in, yeah,
Tell me the page number again.
C 29, C
C29.
28 and C 29.
I wouldn't necessarily know the picture, but I would know what happens. The main one that you want to focus on is the moire pattern,
Okay, okay.
which is C30.
Mhm.
But yes, we will talk about those because it's down the line here when we get to components of a flooring unit and grids. I don't know why they have them so close here. So close, or so early in the chapter, they must have kind of changed the order of it here. All right, do we feel comfortable with CR? So we know that we have to have an image receptor. We know that these image receptors are not gonna be as heavy because they don't have all the electronics built into them. They have to be put into that reader to be able to populate the image on the screen. Slower response time. Is it more or less patient dose for CR versus DR? More dose for CR, that's why we're converting to DR, right? So better for our patient. Yes. Do we need to know how it's read? Exposed to the light.
That's it.
That's what I would know.
That's it. You don't need like the photos, the for that.
Luminescence. So all that's saying, luminescence is light.
Yeah.
And PSP, if you know what PSP stands for, photos emitted phosphor within the image receptor plate. Photo emitted phosphor. So once you expose it to light, photon, light. That's all of it now. Know that you can also erase CR plates, right? So the same way they're red, you can erase them. So that's gonna be covered, I think, in our QA section now. But it's the same way, you can select a blank patient or you can select an erase feature. The downfall, the major downfall to CR versus DR is gonna be you don't know if it's been exposed or not, looking at it. So a DR plate, you're gonna know there's no image on it, we don't have any ghosting. For CR, if I took an x-ray of Marissa and then I forgot about it and I left it outside of the room and somebody else grabs that image receptor, they could take an image over it and we might have some ghosting or a duplicate image. So then I would have to re-expose her. Doesn't happen with DR imaging though, right? DR is very nice, right? Okay, are we good on that one? Plate and plate reader for CR. Let's go into the DR world. I like the video. I didn't necessarily like the person that was reading the information, but I did watch it a couple times just to make sure the information was accurate, and it was. So if you want me to post it, I can. I know he's not the brightest person. Megan said he belongs in a dark room reading. He does read in a dark room. He's a radiologist. So that's why he does that probably, right? All right, so we have two types of DR. We have direct and indirect. With indirect, we have two types, right? So what are the two types of indirect? Let's go there first. Good. TFT and CCD. How about direct? Do we have one or two types? One type, right? Direct is going to be giving you higher spatial resolution. It does have less heat capacity. So like he was saying, with direct, we use that in the mammo world because spatial resolution is of the utmost importance. But we don't have to use a high dose when we penetrate breast tissue because it's very thin in comparison with bone or other solid organs. Even if a person has a mass or some kind of inflammatory breast cancer, it's not going to be anything compared to a bone penetration. So we can use that direct radiography as a source to increase our spatial resolution as much as possible. Also in the world of mammography, you're talking about millimeters versus radiography, we're talking about centimeters or inches. So millimeters when we're talking about breast tissue because we want to find the breast cancer as soon as possible. Versus our world in radiography, we're not reading millimeters of tissue, right? Even if we measure things out in millimeters, it's probably insignificant. If you miss a millimeter of tissue on an x-ray, it's not detrimental. If you miss a millimeter of x-ray or breast tissue on a mammo, it could be detrimental. So that's the difference there. We mainly use indirect. The difference if you use a CCD versus a TFT, and your indirect is just gonna be your manufacturer. You're not gonna know the difference. Just like you were asking me about the transformer thing, you're not gonna know what type of equipment you're working with. Even if you ask the manager of the department, they probably won't know. If you ask the PACS people, they may know, right? Our IT working in the background people. And there's like a chip certification now. I don't even think you take a registry for PACS anymore, so they're kind of separating it to a different type of test. But those are kind of your IT people. They may know what type of equipment you're working with, but we just need to know the functionality of it and how it could be replaced with what. So are we using a TFT or a CCD? Okay, for indirect at least. Where else do we want to go for this? Do we feel comfortable on direct conversion versus indirect conversion from the video, from talking about it? Do we need to go into detail more? Okay, so let's break it down. Direct conversion. What do you guys have? You guys tell me. Made of amorphous selenium. Good. Anything else we need to know?
I put converts exit radiation energy directly to electrical charges, speeding image construction.
Good. So we have no conversion of light to electrons again. We just have straight X-rays being read down. So we have that direct conversion. We have no conversion going on, no indirect. It's directly coming from the X-ray beam to the image receptor and sticking in there, if you want to think of X-rays sticking, rather than being converted through a process of crystallization. Good. Anything else we want to talk about? The image populates immediately almost. What, it takes less than 5 seconds to be able to see what you've taken. The major pro of this is going to be adjusting your image receptor under a patient portably. I've seen registry questions like this where they say, what is the advantage of using a direct system versus a CR? Or what is the advantage of using, no, we're not using film. Yeah, we'll say CR versus DR. If you have a plate under a patient and you're tiling a KUB and it's digital, DR, you can just simply move it over if you missed a little bit of tissue, versus you using a CR system and having to pull it out each time, run it, put it back in, put it back in, put it back in, put it back in. And it's a lot on your back, right? So those DR systems are really nice for portable examinations. If you need to move just an inch or maybe a centimeter so that you're not clipping anything, it's much easier than removing the entire image receptor, running it on the scanner, and bringing another one back. Our dose is going to be less with DR versus CR as a whole. So our patient dose is going to be less with DR than CR as a whole. Do you have different units that you work with if you use CR versus DR? Are your DR plates built in to the equipment, or can you move them? Some are built in, some you can move. Okay, so you probably use CR post-process or CR films for like post-procedures like fluoro, right? Okay. Okay, so we need some DR plates, right? Why can't we use DR for that? It's so much easier. But for cross tables, I'm thinking like myelograms, or for some kind of like KUB, post-processing, things like that. So you would use post-procedure CR films for that one. Let's talk about indirect. Indirect. So we could either use a charge coupled device or a TFT. What about this amorphous silicon that they have here? What about it? It's indirect. You could use it for what? Good. Transfers light to electrons. Light to electrons. So that's how the process of indirect is read. So we're going to have electrons coming in. We have them converted into light. Then we have light converted to electrons to be able to convert it to an electrical signal. That's how we get the image on the monitor. The two types, the only distinguishing two types, or way that you would be able to guarantee that is an indirect TFT system, is our unit in here. You know how you have to plug it in? This one is an indirect TFT over here, an indirect TFT. Does anybody have that clinically, where you actually have to plug in the image receptor for it to be read? Ew, I don't like the design of it. So it doesn't make sense for me. Do you keep it plugged in, or do you plug it in after each image?
It's always.
It's always plugged in. Okay, it's always plugged in. So with ours, the way that it's set up, maybe because it's only used for teaching, it moves, you know, the image receptor moves, so it's not built in. If it was built into the bucky, the wall bucky and the table bucky, I wouldn't mind it. But because we're moving it around, then it has that wire, it's very inconvenient. So every time we take exposures with the juniors, it's a mess, because somebody's almost tripping over the cord. So, it's just not functionally practical, I don't think.
It's only like that in one room.
Okay, and then did anybody find any information about CMOS? So this is the complementary metal oxide semiconductor. I know we talked about it in
That
the
was
video.
one you're gonna look into, did you ever find?
It's not in your textbooks. So did you find information on
It says it results in low noise and high dynamic range, using infrared detection
it? Okay.
to convert image to digital format, the image to a digital format.
Is it used in both types of indirect, does it say? TFT and charge couple?
It just says, it's under the direct,
It's under the direct.
indirect,
No,
sorry,
indirect.
indirect, just
Like the
indirect
new
detection.
version.
Okay, so it's under indirect, okay, good. And then is it used in TFT and CCD, or does it
No,
specify?
it's like the newer system of
It
CCD.
says-
It's the newer system of CCD.
Yeah.
Okay, this makes sense now, right?
Is it like interchangeable?
So, yeah.
So we get to
Flash.
memorize another acronym, right? Cause that's
See,
just what we
but
need to do.
I have the catering book from last year, so
Uh-huh.
that's what I found it in.
Okay,
And it says, the EHP charges the AMA of the TFT, provides improved spatial resolution compared to the CSI phosphor.
right, so that's what she's saying, it's like an updated CCD, so it would be a replacement for a CCD. So CCD/CMOS,
It says it utilizes active pixel sensor technology.
okay. So it's just newer technology, but we're not using TFTs, we're still using a type of CCD, which would be a CMOS.
That was a lot. A lot of letters.
I don't know why that's in there. This was not on the registry the last time I taught this class, so I'm like, what the heck is CMOS? Let me see if I can find this in your textbooks. It's not in there, so I will memorize that for the future, I guess, right? We get to know a different name, so I guess when I teach CCDs this time, I'll teach CMOS as well. All right, and then what about beam restriction? So remember, we're talking about components of a radiographic unit, fixed or mobile. What about beam restriction? Collimators, good, they're our friends, right? You wanna use them when possible. Increasing the collimation would be decreasing the field of view. Okay, so don't get confused there. That's a good way to trick you. Increasing the collimation would be decreasing the field of view. Make sense? All right, I know they like to trick you on those. So memorize that or think about it or talk about it with someone. All right, and then our next section here is components of a fluoro unit, fixed or mobile. So first we talk about image receptors. So we have image intensifier versus flat panel detector. So image intensifier, did you write the actual diagram out or the pieces of the II? I'm trying to find it in my book here. Anybody who has catering, do they have an image intensifier in here?
Yeah. We have the old book though. Ours is on page C62.
C60.
I teach.
That's not 59.
What is
That's
it?
what I have. Yeah.
What page is it?
59.
59. I just wanna track with you guys. Okay, all right, that's a good one. It might be a little confusing to look at this one because of the way it's shaped. So know that they could make it just one box. So it doesn't have to necessarily taper off there. What they're showing you is the portal hole to the anode right there in the image intensifier. All right, so let's talk about the pieces of an II. So what's the first layer? Pieces of the image intensifier. The first layer.
The input.
This has the glass envelope. I know we don't normally talk about that. All it's gonna do is provide the vacuum for the image intensification. So the first layer is gonna be what? Input phosphor. What does the input phosphor do?
Absorbs them, photons, light photons.
Good, absorbs them, converting them into light. So input phosphor into light. Typically comprised of cesium iodine. I would know that, the composition of it. Cesium iodide, what it's made out of. All the other stuff on this I wouldn't know, but I would know the purpose of it, and then it's the first initial striking. The first initial striking of the image intensifier is gonna be your input phosphor. So what are the x-rays gonna hit first? Unless, of course, they give you glass envelope. It would technically be a glass envelope, technically, because it's protecting it. Input phosphor is gonna be our first layer, so where do the light photons go from there? Photocathode, good. What does the photocathode do? Good, light to electrons, photo, light to electrons. So we're converting it there. What is the next place that they go to? Electrostatic focusing lenses, good. What do these electrostatic focusing lenses do?
Helps with magnification,
They can help with magnification, but their main purpose is to focus. So just as the focusing cup streamlines, it puts all of those electrons together, focuses them in to strike the anode opening. So anode is the next place. Remember, it's just gonna be a metal plate with the hole in the middle. It can be rotating or non-rotating. The electrons are then going to pass through the anode, and then where are they going next? Output phosphor, good, which is made of what? Zinc, good. It's made of zinc. And what does the output phosphor do?
Convert electrons into light.
Good, converts electrons into light photons, and remember, what is this whole process of image intensification? What's the purpose of it? To lighten or brighten the image, so we don't have to work in the dark. Okay, and then we have questions on that, or we feel good about image intensifier? You know that the image intensifier is the larger part of the tube. If you're looking at a C-arm and you have this skinny little box over here, but then you have this huge circle over here, your image intensifier is gonna be the huge circle. This is just the X-ray tube. What part do you want to be closer to the patient? Image intensifier, good. So it works just like an image receptor. Feeling good on image intensifier? Okay. All right, flat panel detectors, So they use these a lot in angiography and special procedures. So you might not have even seen one. Anybody seen a flat panel detector fluoro unit? Yeah, they have one at Memorial. That's right, they have one at Memorial. These are so nice. I need to go visit that one. It is an IR, yes. Yep, so if you've seen, even if you look at a fluoro tower in special procedures, it's not gonna have that huge tower on the top, it's gonna be nice and flat. It's just gonna be a thin rectangle.
I think we have one in Cisco also.
Nice. I like it. So what is the difference? What's the difference between an image intensifier and a flat panel detector? What is it? It is digital to an effect, but so is image intensification, because we're not having any film, any analog, or having to run any film. So this is what Kettering says. It uses a more modern solid state detection array as the image receptor. So it's flat versus it being rounded and distortion occurring. We have a flat panel. So just think of like an image receptor. What is it? Probably. Oh, yes. Probably. And then what we talk about next, or what it lists next, is most flat panel detector arrays are indirect solid state systems, X-rays being converted from light and then to an electrical system. So it functions like a direct system. It functions more like a direct system, just like a direct image receptor would. Advantages: lower patient dose, wider dynamic range, and better stability, because it's just flat, right? So better spatial resolution as well.
They have a laser.
What is it?
And they have a laser.
They do have a laser. They're nice. Let's get through these next two sections and we'll take a small break to recap, you guys. Viewing systems and recording systems of a fluoro unit. So viewing systems and recording units, what do we have? Viewing systems, what do you use on a fluoro unit to view the image? A TV monitor, right? So sometimes it's the really heavy. Do you guys have any of the old school TV ones, or are they all flat now?
There's one in
Okay, so they might still have the big ones, might have some flat ones. So we view it on a monitor, so anytime we use a C-arm, we have to have a monitor in the room as well, or we can't view the image, right? There's nowhere for it to go, we have to plug in. That's why it's super bulky. If you use a fluoro tower, so a fixed unit, you already have the monitor in the room, so you just come over here and pull it down so that everybody is able to view it, right? Recording is a capability of a C-arm, fixed or a stationary unit, so any kind of fluoro tower or C-arm, you can record on it. You can do a disc on it to extract the files, or you can send it wirelessly to a computer, which is typically what you guys do in some kind of OR procedure, right? After you do the time, the dose, normally you write down the time and the dose, and then you'll see your tech sending over the pictures. Do they run Cine in the OR? Has anybody ever seen Cine being ran, where they're actually recording a video?
In the
Yeah.
OR.
In the OR, okay. Sometimes they do it in angio, it's pretty cool, like subtraction, things like that. Okay, so I think that's all you need to know with that, viewing systems and recording systems. What about the ABC or AERC? Someone presented on this for fluoro.
Oh, I didn't. It's right there.
There it is, right there. So tell me, just very basically, do we adjust technique or does the C-arm do it for us?
It does it for
It's
us.
automatic.
Does it for us, right? So we use ARRT or ABC, you might see it on the registry. I think they're eliminating ABC and turning more into automatic exposure rate control. There's another abbreviation that we have to memorize. How fun. So variously adjusting the light, variously adjusting the technique based on the needs of the image. So there's set techniques or set brightness controls within the system, in the viewing system, and they would be adjusted by the ABC or AERC. And then magnification mode. I made a boo-boo with this one. I think I talked to you guys about this one. I read it in the textbook the other day. Were you asking about it? It's opposite of what I said. It's
Yeah.
opposite of what I said. Whoever I talked to about it. Alright, so magnification mode, what does it do to the dose?
Increases.
What does it do to the spatial resolution?
Increases it.
It increases it. I told you the opposite. Okay, so I don't want you to think about it at all because it doesn't make sense. It's just something that I want you to deal with, because I have a major problem with it too, because I looked at the technicalities of the pixels and all that, and I've gotta let it go. So I'm letting it go and I'm moving on. When we increase magnification, we increase spatial resolution. So think as you mag up, you're able to see smaller structures, okay? Don't think about the blurriness that's present and the graininess and all the things that are really bothering me about that. We'll just stick to that because that's what the registry wants us to know, right? So I like to think about it as,
A magnifying glass or something?
Yeah, because then it stays clear.
And you can see it's
sure. It doesn't work for me, so I'm trying to associate it with like apex of the patella being at the bottom. Doesn't make sense, but whatever, we'll go with it. We'll go with it, right? Apex of the patella is at the bottom, and that's just what it is. As we increase magnification, we increase spatial resolution, so we're going with that. Magnification mode, since it does increase the patient dose, we don't always want to be running in mag view. We can mag up several different stages. We normally have like ×2, ×4, ×6, ×10, depending on what kind of equipment you're working with. But as you increase the magnification, you increase the dose because you're increasing the concentration of x-rays, right? So we're going from this to shooting the same amount of x-rays, but just right here. So think about we're killing cells, killing tissue, killing organs. We don't want to run on mag view all the time, right? Dangerous stuff. It's also going to increase the heat. So you have an increased risk of radiation burns if you're running long studies. This is not going to happen in typical OR settings. We're used to working with this equipment and we're using low dosage, right? Not always running on mag. Questions on mag mode? Okay, and then we have table. So components of a fluoro unit, when it says fixed or mobile, I'm thinking they're talking about the fixed unit. So the fluoro fixed table. So we know that we have RF rooms, right? So radiography or fluoro rooms that you can shoot both in. What is different about the table in these rooms than a regular radiography room?
You can stand up.
Receptors on the top.
They can stand up. The image receptor's on the top. If you're running fluoro, the tube's gonna be on the bottom. You can also switch it if you're taking a static x-ray. You can put your image receptor in the tube, bring the x-ray tube over and take a standstill picture. Good. What about, radiation protection within the table?
The bucket slot cover, the skirt that you put on.
Good. Bucky slot cover, the skirt that we put on, we talked about these in radiation protection. The table is different, right? The table is much different. We can have attachments, accessories, we have the foot pedal, the straps that we can put on. The lead curtain protects us, and then we have all of those cool buttons that do all of that stuff to fluoro, right? We don't have those in regular radiography rooms. Do your tables raise up?
No.
They still don't raise up, okay. So somebody needs to design that, so continue on your education, become an engineer, or whatever you need to
Or
do.
like a foot
Patent
pedal, like
something.
the foot thing you pull out should be able to raise up, even if they can't raise the table up.
I like it, design it.
What would you
Design it.
raise it up
So you have-
for?
So the patient.
Or raise it up or raise it down for your back or,
Well, if it raises down with that kind of, cause you got the Bucky slot cover, it's supposed to like cover.
the whole table, I would like to move down. I think about these things because I'm short, so I think about if somebody told me to get on that table.
A lot of patients can't, and then we have to slide them over.
Then we have to get on top of the table.
And pull
or
it
get
out.
started on that.
Do you see where there's a need for this? So go on, design it, patent it, go on Shark Tank and make some money.
The location of that, Bucky slot cover, isn't that supposed to be like, to help protect your like gonadal area?
It
So if you move
is,
it down, wouldn't that defeat the purpose?
Just put them on the table and then move it back up.
it is, but the purpose of the Bucky slot cover is the Bucky tray that you move.
Right.
You know how you move it all the way down?
Right.
There's that lead strip to
Yeah.
block all of those x-rays coming out of there. So it would protect whatever level. Yes, it is about at the gonadal region,
Okay.
but even if you move the table, it's gonna block the x-ray that would be coming out of there. It's the ability to move that image receptor Bucky
Right.
throughout the table and still have coverage.
Okay.
All right, let's take a quick break. I know you're dying. Moving along, we have accessories. So we have stationary grids, Bucky assembly, and compensating filters. So let's start with stationary grids. So we'll go back. Audrey said it was like 20, something like that. Yeah. All right. So what is the purpose of a grid? Again, to clean up the scatter. Good. By, how does it do it?
Low energy.
Good. Absorbing the low energy photons, we were getting there. So it's basically like a filter, right? But the grid is attached to the image receptor, right? So it's behind the patient.
Is it the strip?
The strips, yep. Line pairs per millimeters are how the grids are measured or used. Does contrast increase or decrease when we use a grid?
Increase.
Good, increase, we all agree, right? We're taking out that layer of gray or that foggy layer. So we're increasing the contrast. And then Kettering also covers if a grid is off focus or if you have grid errors in here. I wouldn't know all of these. I would focus mainly on the Maury effect. Do you have the Maury effect in your notes? Okay, do you remember what it is?
It looks really
Good, yep.
The residents of the grid, it's the frequency is the X-ray.
Good.
under artifact.
It is grid artifact, yes. So a wave lag, sometimes they call it a zebra stripe, sometimes they call it a watery appearance of an image. A moire pattern. It occurs when two linear grids are placed on top of one another to make a crosshatch. So you have one going this way, and you have one going this way. But the lead lines are not aligned at the right angles to one another. So when you're lining them up, you have more like 45s. So you have one stacked maybe this way and one like this, right? So they're not even, so we have a moire or a wave pattern.
How would that happen? Wait,
It shouldn't happen.
okay.
So error in detection. So when we're using digital imaging, we're using more built-in grids. So this would be a digital error. Unless you stack two grids on top of each other randomly, you wouldn't do that.
Okay.
Right?
Yeah, my mind.
We know how to use our brains, right? Let's see. We don't need to know that about subtraction. And then I'm just gonna read this last little bit. Ooh, this is a good one. The moire pattern can occur In CR, when the laser light reader runs parallel with the area of the grid lines and are projected onto the PSP plate. One way to avoid this artifact is to always use a grid frequency of at least 60 line pairs per centimeter. So if you're using a low frequency grid and then you run it through a CR machine, has anybody ever got a Moria pattern by that happening? I've seen it like one time ever. It's a very, very rare occurrence though. So I would be able to recognize a grid artifact. Do you guys know grid cutoff, like side to side or top to bottom? I would be able to recognize grid cutoff, and I would definitely know the Moray pattern. I would know what a grid does, where a grid is, and know that we can use a grid in all types of imaging regardless of the different type of image receptor. So we can use it in fluoro, there's grids built in sometimes, we can use it on a standing wall bucky, we can use it in a portable if we carry a grid with us. We can use it at the table, because there's a built-in grid to the bucky. Questions on those?
So the past few times I've used a grid, like most in like a cross table hip or something,
Okay.
I get like this like weird artifact that almost looks like it's like part of the grid.
Okay.
Or like part of the.
What does it look like, a line?
No,
or-
it's like a block.
Oh, it's the grid then.
But like, how do you prevent that from showing up?
You get a new grid.
Really?
Yep. Does it happen every time you shoot the grid?
Mostly on like cross table hip, it'll be like right in the center, and like you can't even see the hip.
Is it a grid artifact or?
That it looks like it's not part of the body. It's like something that's in like the.
Shoot the grid plain
Yeah.
without anything. Like put your tissue box on there or something.
Yeah.
Shoot the
It's
grid
very
plane
weird.
and see if it occurs when you increase the dose, because you know you use that high dose for
Right.
cross table lateral hips. I'm wondering
Right.
if once you use a certain technique, you have that artifact being present.
Yeah.
Probably need a new grid.
I don't know why it would do that. It just started happening, but I don't know. It's very strange.
Interesting. Interesting. All right, bucky assembly. Tell me about the bucky. What is it? Holds the image receptor. Sometimes it can hold a grid as well. What is the purpose of it? To hold it. To make it immobilized, right? To hold it for us. We have
line the tube up to it.
good. So you can line the tube up. Yep. We have good. Sometimes they call it marrying. Slang terms using marrying, making them on the same level, or lining the tube up with the bucky receptor.
Also has the AEC. It also has the AEC.
It also has the AEC. Good. I was waiting for somebody to say that. So you have to have the bucky to utilize the AEC, right? So we don't have an AEC built into just an image receptor. You have to have the bucky. That's where the AEC is located, right? You have the chambers, you have the squares, the lineups. Yep.
It says that like when you put the IR in there, like the light will automatically.
Oh, PBL. If we utilize PBL, when we put the image receptor in there, it automatically collimates to the size of the image receptor.
Is it positive implementation?
Yep, positive beam limitation. Good. We don't have a bucky portably, right? I mean, maybe they'll ask you a question like that on the registry. I don't know. Seems pretty easy. They might ask you what is the bucky, or label the bucky in this image if it's an x-ray room. So lots of labeling questions being put into the registry. So put your mouse over the AEC, put your mouse over the grid, put your mouse over what would receive the most dose, put your mouse over what would receive the most penumbra, put your mouse over what would have the greatest spatial resolution. So kind of start turning your wheels thinking about that, the visual identification at least. Compensating filters, do we need to talk about it again? Are we familiar with them? Wedge filters, trough filters, horseshoes, sometimes they
I
call
feel like
them
I've never seen that.
boomerang filters. Okay, let's talk about it. That'd be a good time. I know it's in this book because I just taught it recently.
Different body parts would be imaged differently based on the amount of X-ray energy it gets from them. So you can
Good.
use a compensating filter to increase or decrease exposure to a specific body part.
Good.
I Googled it, I looked at pictures, I just feel like we don't use that.
We don't use it.
Okay.
You're not gonna see it clinically.
Oh.
We don't use it clinically. If you want to read about it though, I will give you a page number in here, cause I know it's in here somewhere. Under filtration.
Would we ask, like, identify them?
What type of, they might ask you, what type of filter would you use on a foot?
Oh,
That would be like a wedge.
A wedge, right? A wedge, based on the shape of the foot.
oh, I guess I better go with that.
She's like, guess I better do that then. I'm gonna try to find it, I know it's in here. It's in your little skinny book here somewhere. Alright, hold on, I'm gonna have to go to the front. Let's see, filtrations.
Stayed right in there for some reason. To get a good description of that one.
So in this textbook, it's on page 36 and 37. 36 and 37. I'll just read you very briefly what they describe in here. Compensating filters can be added to the primary beam to alter its intensity. These types of filters are used to produce an image image anatomical structures that are non-uniform in the makeup and assist with producing a more consistent exposure to the image receptor. So think about the way your foot is, right? I know nobody wants to look at my foot, but here we go. My foot's thicker here than it is here, right? So you could use a compensating wedge filter to even out the beam. You would attach this directly to the actual x-ray tube. We don't have them, we don't use them, right? They are external, added. And what it would do is you would have the wedge being like a triangle. So you would have the thicker part here and the thinner part here. So that way we would have a more even image. Makes sense?
So it's actually like a useful tool to get like a clear image when we don't use them.
Because our techniques are so small, we don't have to.
So it's phased out.
Yeah.
Okay.
We have post-processing, so we don't have to attach things. We just do everything on the computer, right?
Okay.
Another one that they talk about is a trough filter, so TROUGH, trough filter. And the image that they give you is a chest. Like if you were imaging a chest, it has thicker parts towards the outside. So it's thick, thin, and then thick. And it's used to make sure that you have an even, uniform beam exposure in the lung field. So the lungs are very easy to penetrate, so you would have a thicker filter over the lungs.
Just attach it to the,
Yeah.
okay.
Yep.
So chest trough, foot wedge.
Yeah, I would know those two basic ones for sure.
Thank you.
A wedge and a trough. All right, feeling good about those? Filters though, all filtration does the same thing. All filtration does the same thing, so it's gonna be a reduction of beam intensity in some capacity. All filtration is gonna decrease your overall exposure. All right, image processing and display. This is the fun computer stuff that we actually use all the time, right? So image processing and display, raw data pre-processing, and then we have some sections under here, analog to digital converter, quantitation, corrections, rescaling, flat fielding, dead pixel correction, and histogram. So what do we have for these?
Pre-processing takes place in the computer.
Good.
Their algorithms determine the histogram.
Good. Pre-processing takes place in the computer. We don't pre-process, we post-process. We post-process. So the raw image is pre-processed. When it first shows up and it's kind of loading, it looks like it's downloading on our computer screen, that's pre-processing. What about analog to digital converter, ADC?
Analog signals sent through an analog to digital converter to convert info into numerical data.
Good. Why do we need it in numerical value? Computers work in numbers, right? So that's how we determine the shades. So think of it like a pixel system. Good. How about quantization? Quantization.
Process of assigning discrete numeric values to data points.
Interesting. What do you guys have? Anybody else have anything new? Anything different?
Ability to assign a value to each pixel corresponding to the gray shade determined by its bit depth.
Good. So how do we utilize the number that the ADC creates? How do we analyze that to actually be a grayscale? So each one is assigned to one. That is what the process of quantization is composed of. So one might be black, whereas white is gonna be, I don't know, 5,000. And then every shade in between has a different number assigned to it. That's how we actually get the image. Remember, computers work with numbers only, so it has to be digitized to a number format first before we can view it on the screen. Make sense?
I wrote down the, numbers of each bit depth, we need to know that.
Are you talking about the like 0 to 1,000, like that?
Yeah.
I would not know those numbers. Okay. No. I would not know those because we are never going to use the ADC to assign a number. We can't modify it, and it's gonna be different specifically for every machine and manufacturer. So I would not know those. I do know what you're talking about though. Good, so the ADC is gonna sample, quantize the data into numbers and assign it to a grayscale based on that. Do we feel good on those? Corrections. So we have rescaling, flat filling, dead pixel correction. What do you guys have for these? Start with rescaling first.
Overexposure and underexposure correction.
Okay, so rescaling, processing technique used to correct for over or under exposure, rescaling it. So do we do that or does the computer do it automatically? Both. Trick, both. So the computer tries to take account for overexposures or underexposures based on that SI number or that exposure index number, but we can also rescale the image. How about the next one that they give you, flat fielding?
Improve image quality by removing artifacts from
Flat field corrections. I haven't seen this with any software that I've used. Have you? So it is image processing and display, so maybe it's only used with specific manufacturers. I've never seen flat field technique used. Supposedly it can remove the artifact from a 2D image though. So if you have a pacemaker present and you wanna see what's behind it, you should be able to just kinda run your mouse over it and it should remove it for you. I've never seen it. It's interesting stuff though. Alright, and then dead pixel correction.
What is that?
The IR has, if the IR has a dead pixel, it's gonna, the computer software is gonna fill in that pixel based on the surrounding pixels.
Good. So this one's dead in the middle, this one over here is light gray, this one's light gray, this one's light gray, this one's dark gray. It's gonna average those out to be similar factors. It picks up for those dead pixels and just kinda gives us a good image still. Feeling good on those? Feeling good on those? What about the histogram? What is it? What is a histogram?
When you select your body part.
Selecting your body part, good, but it's a table, right?
The LUT.
The lookup table, good. The lookup table is a histogram, bless you. But specifically, do we have anything under image processing and display for this one? For histogram.
Determines the values, determines the median number, automatically rescales.
I couldn't hear you. Tell me again, Heather, I think you're in the right direction.
Determines values of interest, determines the median number, automatically rescales the values of interest.
Good, so there's a histogram for each body part built into your machine.
Isn't it to like eliminate scatter?
It is used to eliminate scatter, and the reason, how does it do that? Tell me how.
So it collimates?
It can collimate using PBL, so that could be one way it can eliminate scatter. But a histogram is going to give you a value of interest that says this is a safe number to use for this part, right? So anytime you do that APR part selection or APT part selection, it's working with the histogram in the back, in the kind of the imaginary computer space of it. The histogram is gonna be a chart, and it's gonna say this is a good value for a hand x-ray. It will give you a range, so this is a small patient, this is a large patient, this is a medium-sized patient, this is where we should be within the range.
So So basically,
essentially
they
just
give you
exposure.
Exposure techniques built into the computer.
Okay.
On a chart, if you wanna classify it like that. Okay. Feeling good on that one? Alright. Moving on, corrected data for processing. So first we have grayscale. What do you guys have?
The new word for contrast.
It is the new word for contrast. Yeah, we're kinda shifting to that. Cassie, what'd you say?
X-ray beam attenuation to the tissue.
Good, so different attenuations are gonna create different grayscale. Grayscale is just gonna be what? Different shades of gray. Different shades of gray. So we know in X-ray, we have to have a grayscale to get an image that's diagnostic. You can't just have black and white. It would be just like the paper that you're looking at. You have to have a grayscale to be able to have a diagnostic image. Kettering says each pixel contains bits of information. The shade of the pixel is known as bit depth, and it's determined by the number of bits per pixel. Everybody know that? Everybody familiar with that? Alright, and then it also mentions the lookup table. So the lookup table is used as a reference to evaluate the raw information and correct the luminance values or the brightness. So we'll make it more bright using the lookup table. There's a lookup table for every anatomical part. That is the histogram that we use, right? The histogram that we use is the lookup table.
Okay, I have a silly question, but, okay, so
Not silly.
the control we use when we're selecting body parts,
Mm-hmm.
and it does the positive being, limitation, all that stuff. Is that,
ARRT.
can that kind of be a lookup table, or is the lookup table internal on the computer?
Lookup table is internal to the computer. So
Okay,
think electronics, post-processing.
electronic post-processing,
Mhm.
okay. Thank you.
You're thinking APT, APR, selection,
Yeah.
part selection, built-in.
Yeah, I think I
techniques.
missed that off. I'm
It's
sorry.
okay. It's okay, we're separating it out. Alright, what about edge enhancement? Edge enhancement,
Improves visibility of small, high contrast areas.
good. Enhancing the edge, right? Increasing the visibility of small images or small objects. Alright, what about equalization?
Image processing using a histogram of the image to adjust the contrast.
Okay, good. How does this work, or do you know anything about equalization? Have you heard of it before?
What did she say in here?
Can you say it again for me, Madison?
Image processing using the histogram of the image to adjust the contrast.
So we're using the lookup table, and the lookup table can control the equalization. It controls the contrast without losing any data on the actual image. So controlling the contrast. So think of it like window leveling, window widthing, those post-processing techniques. It's the section that we're in here, post-processing here. Alright, and then what about smoothing? Smoothing. I had never heard of this term.
I have
I only found that it can negatively impact the resolution.
It can negatively impact the resolution because you filter it. So think of it like a nice filter that you put on Instagram or Snapchat. It smooths everything out. That's exactly the process of it. So the definition.
Sharpness?
So it does take away sharpness, but the purpose behind it is for small structures and gross detail. So if you're looking at something really small, you could smooth the other objects around it to where you're able to focus in on this.
Like blurring the background.
It occurs by averaging all of the pixel frequencies with the surrounding pixel values to remove image noise. Yeah, so it's like a filter. Think of it like a filter. Kettering also says it's spatial frequency filtering.
I have low pass filtering.
I have both.
Okay,
I have
In
both.
this
did you
one.
guys find that in the book? Okay, good. Good.
Should we know the other terms for it?
I would know smoothing since that's used in your registry.
So don't know spatial or low.
I wouldn't know spatial frequency filtering or the other term that Jesse used, that low filtering, or low frequency filtering. Smoothing is the term that the registry uses, so I would kind of associate that. Alright, and then data for display. data for display. So we have values of interest and lookup table. So what do we have for these?
Value of interest is the digital data set of information that is arranged into a histogram distribution.
Good. So a value of interest is going to say on this histogram, it's okay to be from 5 to 20. That's the value of interest, right? We know that the histogram is gonna be the chart, so value of interest is just gonna be what limits it. And then what is the lookup table?
Convert the value
Like a
of
reference.
interest to different numbers to determine the grayscale.
Tell me again, I'm sorry.
Look, it converts the values of interest to different numbers to determine the grayscale.
Good, exactly. So those numbers that we're using, that we're assigning from that ADC are on the histogram. It's also known as the lookup table, and it's converting them to a contrast level. Good.
So a histogram is different from a lookup table, how?
It's not. A lookup table is a histogram. Yep. The specific histogram that we use in radiography is a lookup table. Okay. Very good. All right, let's go post-processing. Post-processing brightness. Brightening the image, right? Remember the old term was density. Density meaning darkness. Now we use the term brightness. So we control how light the image is or how luminous the image is. Brightness, it does define it in here, the intensity of light that represents each pixel on the monitor. So remember, we're looking at an actual monitor here. So associate you with just taking the image, you walk back, you're looking at your picture. This is post-processing, this is where it begins. All right, what is next on here? Contrast.
The difference in light to dark.
Differences in light to dark. We already know high contrast is black and white, low contrast is lots of shades of gray, right? Differences in brightness is going to be contrast. Then we have region of interest or ROI. So ROI.
The value of the objects.
The what?
I put particular importance,
Particular importance, okay? Why?
like the area
That
that's.
area of
Oh,
interest,
okay.
Like you're looking at.
What
a
you're looking
particular-
at.
Yeah, identifying a specific anatomic area on the digital image.
Good. So what do we need, what'd you say, Ethan?
No.
What do we need on the actual image? So we're looking at a chest x-ray, the region of interest. What do you have to have on a chest x-ray? Right, claustrophobic angles, the apices, good. Lateral borders of the lungs, the heart. We're not looking for motions, we're looking for stability in the image. Region of interest, what are you looking at specifically, the boundaries? Sometimes they like to call it the boundaries of the image. You critiquing. Electronic cropping or masking. Electronic cropping or masking.
Example is illegal,
One of them is illegal, yes.
but masking.
Masking is illegal, yep. Cropping is not.
Cropping is like getting rid of like black, nothing that's like anatomy.
Correct. So cropping is gonna be eliminating nothingness for a better image, right? A radiologist are gonna be working in a dark room, so if you have a big white area on the image and you crop it, that's okay. But if you mask anatomy, because you included the abdomen, you did a chabdomen instead of a chest, and then you decide to mask it up. So why is it illegal? Because we've already exposed the patient, therefore the radiologist should be reading what we are actually imaging. And if there's something that the radiologist could have seen to identify as an incidental finding, it puts them in liability, right, for missing it. Because you've already exposed it anyways, masking it's not fixing it, right?
Also, isn't it's illegal to copy an image? Like,
So,
if
yes.
you're taking like a, which I think is weird because
I do too.
Alara.
I know. So the purpose, so the reason why it's illegal, she's
you're
saying
charging
like,
for like 2 pictures, but
Right.
you only took 1.
exactly,
That's what they kind of told me. But then
exactly.
they're kind of like, but you know.
So if you have a hand and a wrist ordered, and you take your PA wrist and just copied it over from your hand, it is illegal, because we're charging the patient for multiple exams. but we're not actually taking the pictures.
Are you doing all the radiation?
Then you're double exposing, right? So maybe it needs to be a conversation that you have with the doctor, like maybe you should order something different, but that's a lot of time and people don't wanna do that, so they're re-exposing the patient or they're copying over it legally.
Yeah, I had a hip, pelvis, and then a femur, and then the frog leg 2 times, I was like,
Same images over and over and over and over again, right? Yes, though. Yes, I agree with you. Okay, stitching. When do we use stitching for? Scoli, right? So that's our most common one. What is stitching? Putting 2 or more images together. So there is a post-processing stitching technique that I've seen used for like tiling abdomens. It's only available through certain software. So if you took like 4 or 6 images for 1 KEB, basically, you could stitch it together. So you can do some overlap there. Mainly we use it for Scoli, right? All right, display monitors. So viewing conditions, viewing angle, and ambient lighting. What did they get into detail here about? What did they get into
Certain
detail?
monitors have a certain viewing angle, you have to be perpendicular to the screen to see it. Newer TVs have a wider viewing angle.
Does it tell you that specifically in our textbooks or is
I didn't find anything about angle, I found the ambient lighting.
ambient
I couldn't
lighting?
find.
Ambient lighting's for better visualizations for your rods and cones for viewing. I could see that.
Right,
There
what
is an
that
angle
light.
requirement, but I don't know if it's actually specific for radiography. I know they have really strict viewing conditions for MAMO. Did you find it in a textbook? No, you just know it. You just know it. Did anybody else find anything for angle? Viewing angle, viewing conditions, viewing angle. Is it in Kettering?
No.
It just says viewing angle. That's all.
A bad TV will have a narrow viewing angle.
It refers to the maximum angle at which a display monitor can be viewed with acceptable visual performance.
Right, but is it gonna be specific to each manufacturer, or is there, okay,
So like the newer TVs are, like,
Yeah.
when big screens first came out, like a lower quality one would have so you have to be more in front of the TV to see it, and then you move to the side, like an older phone does the same thing. You look to the side, you don't see the screen as well.
is there a specific angle though that we know, or,
And the bigger it is, the 180 the better.
okay. I don't have anything for that.
Same.
Probably at least 45 degrees, I would think.
I would say at least 45, yeah, but I don't know a specific angle to give you.
Probably too varied based on the different monitors.
I know when you get a new monitor, so here's the rules as far as QA and QC go. When a radiologist gets a new monitor, us as the technologists, we don't have to have specific viewing conditions because we don't read, right? So we're just checking our image, it's okay, whatever, we're good to go. But a radiologist is actually reading. You guys know when you go into the dark room, it's dark, you have ambient lighting, and their monitors are QA'd and QC'd every 2 weeks. So somebody goes in there, cleans off all of the smudges, make sure the lighting's good in the room, make sure that the grayscale is good. So they go in and they do all of this QC on the machine, on the actual viewing monitor.
They pick up the pizza crumbs too.
They probably pick up pizza crumbs too, right? They clean off the magnifying glasses. So I only know this because one time I was a QC tech at a MAMO facility, and we had somebody that came in externally and did it. But it was a requirement. It's super strict in MAMO because they don't want anything on the screen, and they wanna make sure that the grayscale is good, the contrast good, brightness is good. I don't know about the limitations for the angle though. So, but if there was a new monitor put in, the radiologist is gonna be trained where they need to sit, where they need to read, and proper lighting. I wouldn't get into the specifics of what we're doing with that. Our viewing conditions are not very good, right? We're treated like a little black sheep. We're going to take the pictures.
I have a question.
Yes,
What is the difference between, shuttering and like actual collimation?
shuttering and collimation. Shuttering is typically automatic,
Okay.
so not controlled.
Okay.
But shuttering is normally specific to interventional radiography
Okay.
and cine imaging. Yep. All right, where did we leave off? spatial resolution, then we have pixel size and pixel pitch. We already kind of talked about it a little bit. Tell me, how does pixel size affect spatial resolution? Good, inversely related, right? Inversely related. And then what about pixel pitch?
Pixel pitch and pixel size are equal.
Good, good. Pixel pitch and pixel size are equal, so the middle to the middle of another one. Good. The middle to the middle versus the edge to the edge. Brightness and contrast under display monitors. Brightness and contrast. What do you guys have written down for this one?
The leveling, the
Window-
brightness, and the window width.
Good, so let's talk about window level first. What does window level do?
Exposure.
The brightness, good. So I like to think about blinds. Your window level affects the brightness. So if you open the blinds, it gets brighter. If you close the blinds, it gets darker, right? What about window width? The contrast. So the window width affects the contrast. So you guys specifically use both of these, well, don't specifically use one of these without the other. So you probably aren't familiar with which one affects which. Because when you move your mouse and click, it adjusts both. So you have window leveling and window widthing when you're moving your mouse post-processing. But I would know the difference between the two. Remember, the level is gonna be the blinds and the brightness. The window width is gonna determine the grayscale. And that's gonna be a post-processing technique. Anything else that we have under this, brightness and contrast? I think that's what they want you guys to know. All right, let's move on. Imaging informatics, imaging system, HIS, example HIS, RIS, EMR, EHR. So let's start with HIS.
HIS. That's something.
Hospital information system.
Hospital information system, good. So not specific to radiology. We can share everything, right? Okay, what about RIS?
Radiology information.
Good, radiology information system, that is for us. An example of a RIS is PACS or DICOM, okay? RIS is an example of PACS or DICOM for us, our networking systems. How about EMR, what is it?
Electronic medical record.
Okay. Allows us to view everything of the patient's chart on a computer. It's electronic. Very inconvenient when we have downtime though, right? We have to go back to Stone Age and we don't know what we're doing or who we're grabbing or what's on their chart. But it does result in less repetitive exams because we're able to see when the last time a person had a chest x-ray versus digging through a chart. And it's more accurate in finding allergies, right? So it's quicker for us. And then what about EHR? Electronic health record, which is very similar to electronic medical record. Did you find a difference, a distinguishing factor?
I think I read somewhere like one on the inside of the facility, and the other one AC from facility to facility.
Oh, okay.
And I can't remember what.
So electronic medical record is probably internal. Electronic health record, you could think of teleradiologist, probably is how you would distinguish those. I would just know the basics, what the systems do, what information is included in them, who has access to them. Right, remember, we practice HIPAA, so it's a need to know basis. So we're not prying around in our neighbor's charts or anybody else's business that we don't need to be in. Anybody else, anything else for information systems? No, feeling good on those? All right, networking, PACS and DICOM. So what do we have for PACS?
Can receive, store, distribute, and display digital images.
Okay, good. And what does PACS stand for?
Picture archival communication system.
Good. Consists of digital acquisition equipment, workstations for displays and manipulation of imaging, and interconnected storage devices that communicate over the network using language useful to DICOM. So let's talk about what DICOM is. First, what does it stand for?
Digital imaging and communications in medicine.
Good. digital imaging and communicating in medicine, DICOM. They do have certain standards that we have to follow and regulations, that we can't share information all over the hospital, and it has to be secure. So what is the difference between DICOM and PACS?
PACS and imaging modalities.
So DICOM is the communicating factor, right? So DICOM allows us to communicate. Picture archiving. Our PACS system is used by DICOM, but DICOM overall is gonna be the way that the systems communicate with each other. So that's why they group them together. DICOM is the way that the systems communicate with each other, so we use DICOM to transfer our images from PACS to the electronic medical record. How they are sending the images over. And then downtime procedures, do you have anything for this one?
I just know it will depend on which systems or systems are non-operational.
Yeah. So downtime procedures or process, it's gonna be specific to where you work, what you utilize, what systems you use, what's down. Usually they have forms or they have stickers and markers ready for downtime. No one likes it, but we all get through it together. It's usually 12 hours. If you work overnight shift, you're gonna work a downtime shift one time, because those are the people that get stuck with it. But there is a process and a protocol in play, depending on where you work and what is down specifically. So if your electronic medical record is down, but your PACS isn't down, you can't look up information from the chart, but you can talk to somebody about the patient. They'll have like a face sheet printed out of all of the basic information. You don't have to manually type stuff in. So it's just gonna depend on what's down, right? There is a protocol in place though. All right, the next section here is pretty short. Do you guys wanna push through? Let's push through.
Fast forward.
They're like, yes, quickly. Okay, quality control of imaging equipment and accessories. Okay, beam restriction. Beam restriction, so light field to radiation field alignment. What the heck are they talking about? So remember, we're talking about quality control now.
Visible
Those are
light,
2%.
it's over the same path as the actors, as you call them, it's gonna move visible light, you can see with your eyes.
Good, it needs to be within 2%. It needs to be within 2%. There's a regulatory number for that, 2%. I would know that, 2%. And the reason this is important is because when the physicist comes out to do QC on your machine, they're going to measure it. And if it is not within 2%, it's 2% or greater, they're going to make you have maintenance on your machine to fix it. Because you could have overexposure of the patient, right? It's not directly lining up. Do you know how to separate QC versus QA? Do you know the difference?
What we do versus what somebody else will do.
QC is gonna be machines. QA is patients. So QC is machine control, QA is patient. So quality assurance, if you hear that term, quality assurance is gonna be patient. Quality control is gonna be machine.
Control machine.
Yeah.
Assurance.
Assurance is the patient, yeah. So if you really think about QA, it's gonna be something with like patient positioning or patient interaction. But QC is always machine driven. So something that we can calibrate or adjust on the machine. All right, central ray alignment. Central ray alignment, what do you guys have for this one?
Should be directed to the center of the image.
Is it 2% again? I don't have a percentage for this one, but it should be directed to the center of the image receptor. If your CR is off, if your CR alignment's off, your SID alignment's gonna be off though. So they're gonna pair. All right, what about recognition and reporting of malfunction?
I should always report malfunctions.
I
Know your equipment, so you know what you're looking for if it's wrong.
Right, so if your machine is suddenly like super hot one day when you're working with it, you should probably call someone, right? If it's not normally that hot. So we have backup timers, protections in play. You guys know about the red button on the wall if things are going haywire, right? Never touch it unless you're dying, right? Never touch it unless you're dying. So, You touched it?
Not on the one on the wall. I
Oh.
hit the red button on the table and shut the whole room down.
We touched it.
I was trying to lock the table.
You touched it too?
There's been a lot of
Sometimes we have
students who
to.
hit it with their head, cause it's like right on the walls you walk by in South. And like the new students, when they're like late, they always, it's happened a lot.
And then sometimes the room just won't work and they're a little overexposed, like it'll just keep exposing, so we have to turn it off.
Oh my god.
Yeah. No, they've been.
Yeah, the
before
CR
all
doesn't
the
line up with the wall.
physicists.
They need a new room.
No, they need a new room. They have
So
to.
do not go to South for your x-ray.
Our new ER room's really nice though.
It's a floor.
Alright, so we always wanna write down if something's malfunctioning, we wanna call the right appropriate people. Your kind of chain of command is gonna be your leader, your supervisor, then your manager, your director within the facility. And then of course, if you wanna get dirty, you can call OSHA or NRC. You might not have a job, but at least you're safe. Alright, digital imaging receptor system. So we have maintenance, detector calibration, plate reader calibration first. So what kind of maintenance is required on that detector calibration? Have you guys ever did a calibration?
I've been checked.
Take out the.
Because you dropped it?
Yeah.
Me too.
Because you have dropped the image receptor, so it has to be recalibrated?
You put it on the floor.
Like on the portable, you have to sit there and they said keep pushing it. It's like they're gonna process it.
Okay, so we know that some of this equipment requires recalibration. The moral of the story is never drop the image receptor, right?
There's like a little metal thingy.
Alright, what about plate reader calibration? Plate reader calibration.
Is that where they put the metal thing on the tube and line it up with the computer? See how off you are?
Typically, it's for the CR machine.
Oh.
I think it's for the CR machine.
There's one they do at Nassau, there's a guy, and he does it all the time. And it's, yeah, he says he's calibrating the accuracy of the CR with the plate.
Oh, that's gonna be the CR, the central ray alignment then.
Okay.
Yeah, that's gonna be the central ray alignment. I'm thinking what they're talking about with plate reader calibration is gonna be just maintenance on the actual reader for the CR. So sometimes it needs to be cleaned, right? Inside of that, where you run it through, the lasers can get dirty, there can be dust involved, so there's a cleaning and kind of a process to doing that. We don't do it. We don't calibrate any of our equipment like that. We don't measure anything, but the physicist will do it, or your QC person will do it. Do you have a QC person that you know in your department?
Yes.
Yes. Okay, so that's gonna be the person who should be overseeing that. And for JCO, it's a requirement that you have documentation of that. Just like when you run your lead through annually to make sure there's no cracks. It's the same kind of concept. Alright. QC test. So erasure, thoroughness, plate uniformity, and spatial resolution for the QC test. So what do you guys have for these?
Probably scan a blank, DR, plate, IR, make sure it's blank.
Good. Make sure it's actually erasing the image. Annual or biannual? Annual or biannual? Let me see if I have something over here for specific. I believe it's annual for erasure. Erasure for thoroughness. What a word. So what they tell you to do for this QC test is they say, make an exposure of a thick lead block, erase the plate, and make a second exposure without the lead block, and verify that the absence of the ghost image of the lead block from the first exposure is gone, right? So you're just making sure you're not having any ghosting. And this is gonna be for CR specifically, remember. And then we have plate uniformity. It says it's performed to ensure that there is a uniform response of the plate and it's free of artifacts. So hopefully you're shooting towards the center of the image receptor and there doesn't need to be uniformity, but maybe you're not, maybe you're using the edge for some reason. And then for spatial resolution, Kettering has, it tests the contrast limits of the system, high and low, to determine the system's ability to resolve details. Do you guys have anything else for that one, spatial resolution?
Can be monitored by imaging and wide paired resolution test tool.
Okay, line pair per millimeter test result, that makes sense, because that's what spatial resolution is measured in. So these tests, we could technically perform all of these, but your QC tech is gonna be performing these and documenting them every year, because it's the requirement of JCO. And then when the physicist comes in once a year to make sure your machine is up to standards and functioning well, they will also do all of these tests and see if you're tracking. So don't just copy over the prior week's number, right? We wanna do actual QC. Display monitor quality assurance. Look how we shifted words here. Quality assurance, because we're dealing with patients now. We're dealing with actual patients. So grayscale, standard display function, and luminance. What do you guys have for these? Display monitor quality assurance.
For like an overall thing, I put, assure consistent display performance and identify problems before they become clinically significant.
Okay, good. Make sure the monitors are functioning, make sure the radiologist can read what he needs to. We've kind of gone over this before though. Usually this is gonna be an assigned task for someone. Grayscale and luminance can be tested. And like I said, it's probably gonna be a QA or a QC tech doing it from these monitors. Shielding accessories, so we have testing lead, apron, and gloves. How often do we need to test these for QC? Annually. Good. How do we test them? Fluoro or x-rays. We look externally for any rips that might be present. Another task that you could do is lifting up your lead. If you feel a heavy weight at the bottom, it's probably not solid anymore, right? If it feels much heavier at the bottom than the top, it's probably leaking down. Probably want to invest in some new lead. I've found cracks in lead pieces over the years. What we do is replace them. We don't donate them. We destroy them, get rid of them, because you don't want anybody else to use them. But typically they last at least 5 years. And we know that the new lead that's coming out is thinner, lighter. That's the lead that we want to use for our backs and longevity. But you do the same thing for any piece of lead. So aprons, thyroids, gonadal shielding, gloves, anything that you would be using to protect yourself or a patient, you have to test annually and document it. Good. And you won't get in trouble if you say this piece had a crack in it and we're throwing it away. You didn't know before you had to do the test, and you're only required to do the test annually. So other than that, we're gonna depend on the lead to work and do its job.